live classes for GMAT. Right? Today we'll be starting with one very useful but elementary concept. We'll start with GMAT quant number properties, and in number properties we'll just focus on one thing today, which is LCM and HCF. LCM and HCF on two counts, it's very important. One, you'll be using that concept in quite a few questions. I wouldn't be wrong if I went ahead and said that probably about 7 to 10 out of the 37 quant questions, at some level you'll be finding out LCM and HCF. So the how-to part of LCM and HCF is definitely a must-know for all of us. More importantly, 3 or 4 out of those 10 questions will involve deeper concepts about LCM and HCF. So it's not just the how-to that is important to us. What is equally important is why is that method working? When to use LCM and HCF? Because a lot of these questions are also going to be word problems. No one is going to come to you and say that, hey, this question, it's a word problem, but what you actually need to find out is an LCM. That's not going to be told to us. We need to figure out when to find out LCM, when to find out HCF. So let's find out some kind of an idea, a marker, something to tell us when will a question be a HCF question? When will a question be an LCM question? What I'm going to be doing is I'm going to be dividing this session into 3 parts. The first part, which I think will run for about 20-25 minutes, will look at the concept area. It's a class. We're actually going to be learning what LCM is, HCF is, how to find LCM, HCF, so on and so forth. Part 2, we'll work on questions. These are problem-solving questions, relatively the easier variants that you're likely to see. Finally, we'll wrap the session, which is the third part, with DS questions on LCM and HCF. And those questions, a couple of them are quite challenging ones and very interesting ones, and would actually test all that we have learned about LCM and HCF till that point. Right? We'll get started with this intro. I'll share the screen and come in between at the end of the concept session to basically wrap things up and then move on to the question part of it. Right? I'm going to share the screen. Just take a couple of minutes to put everything in place. Yeah, is everyone able to, I presume you're able to see the screen, and is everything working and is it in order? Right. Let's get started. We'll look at the first concept we're going to look at is the highest common factor. What is it? Right. We'll start with this word factor. What is a factor? And then move on to the HCF and how it works. Factor. When is B a factor of A? When will we call B to be a factor of A? When B divides A into integral parts and leaves 0 as a remainder. For example, is 2 a factor of 8? Yes, certainly. 2 will divide 8 into 4 equal parts. It's dividing it into integer parts and the remainder is 0. In other words, if B divides A and you get a quotient which is an integer and a remainder which is 0, then it is a factor. Let's start with an example. Let's understand it using an example. Let's find out the highest common factor of 36 and 48. The first step that I'm going to do is I'm going to list down factors of 36. What are all the factors of 36? 1 is a factor of 36. Whenever you list factors, also have this one idea in mind. Always list factors in sets of 2 numbers. If 1 is a factor of 36, 36 is certainly a factor of 36. Find its corresponding factor. You can use the word find its conjugate factor. The next factor that we're going to look at is a 2. If 2 is a factor, 18 has to be a factor. Similarly, if 3 is a factor, 12 will be a factor. 4 is a factor, 9 is a factor. Finally, 6 is a factor. These are all the factors of 36. Now let's list down factors of 48 because we're trying to find out the highest common factor of 36 and 48. Factors of 48 will run through the same process. 1, 48. 2 is a factor of 48. Therefore, 24 is a factor of 48. 3, 16. 4, 12. And then finally, 6 and 8. These are all the factors of 48. The next step, we have listed down factors. Let's move right to left. Let's pick factors which are common to both 36 and 48. What are all the factors common to 36 and 48? 1 is a factor common to both. 2 is a factor common to both. 3, 4, 6. These are all the factors common to both 36 and 48. Oh, I missed out one more, which is a 12, right? 12 is also a factor common to both. The largest such factor, this is the first of the terms. We're coming from right to left. So let's pick it the last. The largest of these common factors, 12, is the HCF of these 2 numbers. So this is the idea. We're picking factors of 36. We're picking factors of 48. We're listing down common factors. We're picking the highest such factor. This is the idea behind HCF. Obviously, this is not the best way to find out LCM and HCF of numbers. Let's look at an alternative way to approach and find out the HCF. As with most things in number properties, your starting point is always going to be prime factorizing numbers. Let's start by prime factorizing 36 and 48. 36 is a 6 into 6. 6 is not prime. We can write it as a 2 into 3. So 6 into 6 becomes 2 into 3 into 2 into 3. That's nothing but 2 square into 3 square. So prime factorized 36. It's prime factorized 48. 48 is a 16, which is nothing but 2 power 4 into 3. We realize that the HCF, let's say H is the HCF of these two numbers, that HCF H has to be a factor of 36. It's a factor which is common to 36 and 48 and the highest such common factor, which means it's a factor of 36. So this HCF has to divide 2 square into 3 square. So HCF cannot contain a prime factor other than 2 or 3. If the HCF had a prime factor, let's say 7 in it, obviously it cannot divide 36. Similarly, the HCF has to divide 48, which essentially means it cannot contain a prime factor that is not present in 48. Prime factors of 48 are 2 and 3. So the HCF cannot contain a prime factor which is other than 2 or 3. So the idea right now we are driving is the HCF has to have only those prime factors which are prime factors of 36 and 48. It should be a prime factor of both 36 and 48. In this case, both these prime factors, 2 and 3, ended up being prime factors of 36 and 48. So step 2, we're going to be listing down prime factors common to both the numbers, which is 2 in 1. One of the common prime factors is 2. The other one is 3. Now, third step, having listed it down, if the HCF contained, for example, let me say the HCF is going to have a 2 and is going to have a 3. If the HCF had a 2 power 4 in it, for instance, will it be able to divide 48? Certainly, because 48 is a 2 power 4 into 3. If the HCF contained a 2 power 4 in it, it certainly will divide 48. But will the HCF containing a 2 power 4 in it be able to divide a 2 square into 3 square, which is 36? It certainly cannot, because it has more powers of 2 in the denominator. So it brings us to the third step. The prime and common the common primes that we have cannot have more powers in it than what is required to divide each of these numbers. Put another way, each of these prime factors have to be picked in their lowest powers that we find in these numbers. Right? What is the lowest power of 2 that we find in these numbers? The lowest power of 2 that we find in these two numbers, one is a 2 square, the other is a 2 power 4. So we're going to be picking a 2 square out of it. What is the lowest power of 3 that we find here? That is going to be equal to a 3 power 1. The last step gives us a HCF, which is nothing but the product of these two. HCF is equal to 2 square into 3 power 1, which is equal to 12. Quickly consolidate this entire thing in a printed form. These are the 3 steps. First step to finding out the HCF is prime factorize the given numbers. Second step, pick only prime factors which are common to both these numbers. In this example, 2 and 3 were present in both 36 and 48, so picking both of them. Third step, pick these prime factors in their lowest power. What is the lowest power of 2 between these two numbers? It's a 2 square. What's the lowest power of 3 between these two numbers? It's a 3 power 1. So HCF is a product of 2 square into 3, which is equal to 12. Quick recap, 3 steps. Prime factor is a number. List down the prime factors. The HCF is nothing but the product of the common primes in their lowest power. Let's look at the second concept, which is LCM. Just hold on for a minute before I share that with PPT. We'll again start pretty much the same way as we did with HCF. We'll understand what least common multiple is. We'll start right-wise. It is a multiple, it is a common multiple, and it is a least common multiple. So we're going to be starting with listing down multiples of numbers for which we are going to find out the LCM. Let's pick an example. Find the least common multiple of 20 and 24. Let's start by listing down multiples of 20. Let's go up to some 10, 12 multiples of 20 without batting an eyelid. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240. I think we run out of screen space. We'll stop here. List down multiples of 24. 24, 48, 72, 96, 120, 144, 168, 192, 216, 240. Got enough of these multiples in place. We got multiples of 20, multiples of 40. Let's pick multiples that are common to both these numbers. 120 is one such number. It's a multiple of 20 and a multiple of 24. 240 is another number, which is also a multiple of 20 and 24. So you can go on listing numbers in this order. 120, 240. The third one, you would have guessed it right by now, which is a 360, 480, so on and so forth. The first such common multiple, the least common multiple, is 120. So this is the idea behind LCM, right? You list down multiples of one number, you list down multiples of the second number, list down multiples which are common to both, and then you pick the smallest such number. We understood what LCM is. Let's again go on and find out how to find out the LCM. The how is very important because we're going to be using it in many questions. First step, prime factorization. Anything to do with number properties, I think your starting point is going to be prime factorization. So get comfortable with this idea of prime factorizing numbers in a jiffy. 20 prime factorizes as a 4 into 5. 4 is not prime, so it's going to be 2 square into 5. 24 is an 8 into 3. 8 is not prime, so it's going to be equal to 2 cube into 3. We have prime factorized both these numbers. Now, LCM of both these numbers is going to be, it's a common multiple of both these numbers. So it is going to be a multiple of 20 and it is going to be a multiple of 24. If it is a multiple of 20, the LCM needs to contain 2 square into 5 in it, because any multiple of 20 will certainly have 2 square into 5 in it. Similarly, the LCM is a multiple of 24, so it needs to contain 2 cube into 3 in it. So in terms of just the prime factors, the LCM needs to have any prime factor that you find in these two numbers. So the LCM, after having prime factorized it, the second step is we're going to be listing down all prime factors that we find in these numbers. What are all the prime factors that we find? 2 is a prime factor, 3 is a prime factor, and 5 is a prime factor. We have listed all of them down. It's a multiple of these numbers, which means the LCM as a number is divisible by both 20 and by 24. If it is to be divisible by 20, the LCM has to have 2 and 5 in it and needs to have a 2 square and a 5. If it is to be divisible by 24, it needs to have a 2 and a 3 and it needs to have 2 cube in it. If it did not have 2 cube, a 24 cannot divide it. So it needs to contain a 2 cube. A 2 cube into 5, is it divisible by 20? Certainly yes. A 2 cube into 3, is it divisible by 24? Certainly yes. So LCM is going to be 2 cube into 5 into 3. So you probably guessed what we are driving at. You need to pick these prime factors in their respective highest power. Unless it is available in its highest power, the number that it contains in its highest power will not be able to divide it. So third step, having listed down the common prime factors, we're going to be writing these prime factors in their highest power. Highest power of 2 between these two numbers is a 2 cube. For 3, it is 3 power 1. And for 5, it is 5 power 1. So having done this, the next step will give us the answer, which is a product of all of these three things. So LCM is equal to 2 cube into 3 power 1 into 5 power 1. 2 cube into 3, 8 into 3, 24 into 5, which is equal to 120. Quickly recap all of these steps. First step, prime factorize the numbers. Pretty much the same as what we did with HCF. List all primes. In this case, you're not going to be picking the common multiple needs to have, it's not the common primes. For the common multiple needs to have all the primes in it. And it needs to have these primes in their highest power. LCM is nothing but the product of all of the prime numbers in their highest power. Let's quickly find out what these two steps are in 2 sentences. For HCF, it's a product of common primes in their lowest power. For LCM, it is product of all primes, not common primes, all primes in their highest power. Right? So have this perspective. It kind of sums up how to find out the LCM and how to find out the HCF and what these two stand for. Let's look at some interesting properties of these numbers, which gets tested quite often. Move on to the next slide. Just give me a minute. just get some quick practice. Right? Try out these two questions. Take about half a minute to find out the LCM and HCF of these two numbers. Both these numbers have been prime factorized for your convenience as you start. Okay. So just to get you comfortable with this idea, let us wrap it up. To find the HCF, you need to list down only prime factors which are present in both the numbers. What are the prime factors common to both the numbers? 2 is present in both the numbers, so let's pick 2. Is 5 a part of both the numbers? Certainly yes, let's take 5. 7 is present in both the numbers, let's take 7 as well. 13 is found in the first number, 17 in the second number, so those are not common primes. We are not going to be taking them. Let's pick these primes in their lowest power. Lowest power of 2 between these two numbers is a 2 cube. Lowest power of 5 between these two numbers is a 5 power 4. Lowest power of 7 between these two numbers is a 7. So HCF of these numbers is 2 cube into 5 power 4 into 7. Quickly move on to LCM. The LCM of both these numbers, definition of LCM, pick all primes. So blindly let's list down all the primes. 2, 5, 7, 13 coming from the first number. 2, 5, 7 already listed from the first number. So all that we need to write from the second number is 17. So I've listed down all the primes that are found in both these numbers. Pick these primes in their respective highest power. Highest power of 2 between these two numbers is a 2 power 5. Highest power of 5 is a 5 power 6. Highest power of 7 is a square of 7. 13 and 17, we're going to be picking them as they are, which is 13 power 6 and 17 cube. So the LCM is a product of all of these numbers, which is 2 power 5 into 5 power 6 into 7 square into 13 power 6 into 17 cube. Quickly see it in a printed form. This is the HCF and LCM of these two numbers. We'll go one step further. Without using numbers, let's just use variables and get comfortable. Again, take 30 seconds to wrap this question. Find the LCM and HCF if A, B, C, D, E, F are all prime numbers. Right, we'll quickly run through the process here as well. HCF lists down only common primes. The common primes between these two numbers are A and B. List those primes in the respective smallest power. Lowest power of A is equal to 5 of A power 5. In the case of B, it is B square. So A power 5 into B square is the HCF. Let's move on to LCM. We'll be listing down all primes. So that will be A, B, C, D from the first number. A and B have already been listed. Let's go with E and F from the second number. Pick these primes in the respective highest power. Highest power of A is A power 7. Highest power of B is B cube. In the case of C, D, E, F, because they are present in only one of these two numbers, let's write their powers as they are. C square, D power 5, E power 1, and F cube. Right? So the LCM of these two numbers is A power 7 into B cube into C square into D power 5 into E into F cube. The answer in a printed form. Right? So we got an idea about how to go about it. We did two simple examples. First step, prime factorize, and then go about whatever we did to find out the HCF and the LCM. Let's look at some interesting properties. The first one is we have found out LCM and HCF for numbers which are whole numbers. We found it for a 20, we found it for a 24. We found out for numbers where we prime factorize those numbers. Do we have LCM and HCF for fractions, and how do we go about it? We can find LCM and HCF for fractions. The first step is express these fractions in their least form. What do you mean by that? Here is an example. If you have a number which is, let's say, is 7 by 175, do not use this fraction as is. This fraction can be written in its least form as 1 by 25. Right? Cancel all common factors and bring it to its least form, irreducible form. That's the first step. If you do it without this, what you'll actually be getting will be a common multiple. It is not necessarily going to be a least common multiple. So the first step is to get these fractions into their least form. After getting that, the next step is using this formula. LCM of fractions is LCM of the numerators divided by HCF of the denominators. Let's consolidate this entire idea with a simple example. Let's find out the LCM of 2 by 3 and 4 by 9. 2 by 3, is it in its least form? Certainly yes. Is 4 by 9 in its least form? There's no factor common between 4 and 9. So it is also in its least form. We're trying to find out the LCM of the fractions. First step, LCM of numerators. What is the numerator? The numerator of the first number is 2. Numerator of the second number is 4. So let's find out the LCM of 2 and 4. LCM of 2 and 4 is equal to 4. Let's find out the HCF of the denominators. HCF of denominators is HCF of 3 and 9. Common to 3 is 3 because 3 is a prime number. 9 gets prime factorized as 3 square. So factor common between 3 and 3 square is a 3 in its lowest power, which is equal to 3. So what is going to be the LCM of these two fractions? It is going to be LCM of the numerators, which is a 4, divided by HCF of the denominator, which is equal to 3. So 4 by 3 is the first number, which is a multiple of both 2 by 3 and 4 by 9. Quickly check it out also. Let's list down multiples of 2 by 3. Multiples of 2 by 3, for example, multiples of 2 would have been 2, 4, 6, 8. We're going to be multiplying the first number with a 2 and then with a 3. Let's do the same job here. 2 by 3 is the first multiple of 2 by 3. 2 times 2 by 3 is a 4 by 3. Then it would be a 6 by 3. It would be an 8 by 3, so on and so forth. These are multiples of 2 by 3. Let's do multiples of 4 by 9. 4 by 9 is the first multiple. 2 into 4 by 9 is an 8 by 9. 3 into 4 by 9 is a 12 by 9, which is nothing but a 4 by 3. So 4 by 3 happens to be the first multiple that's common to both these numbers. So when you list it down, what we have done seems to match with it. So this formula is not something that's been pulled out of thin air. It seems to make sense. Quickly see it in a printed form. Find the LCM of the numerators, which is a 4. HCF of the denominators, which is a 3. So the LCM of these two fractions is equal to 4 by 3. Now how do we go about finding out the HCF of fractions? Just reverse the formula. HCF of the numerators divided by LCM of the denominators. We'll have to find out the LCM, the HCF of 2 by 3 and 4 by 9. We realize these two numbers are already in their least form, irreducible form. Let's start with the HCF of the numerators. HCF of 2 and 4. 4 prime factorizes as a 2 square. So only common prime between these two numbers is 2. In its lowest power is equal to a 2. Let's find out the LCM of the denominators. LCM of 3 and 9. Prime factorize 9, which is going to be a 3 square. 3 and 3 square, list down all prime factors, which is a 3. Their highest power, which is equal to 3 square. So this is going to be equal to a 9. So the HCF of these two fractions is equal to HCF of the numerators divided by the LCM of the denominators, which is 2 by 9. Quickly again, let's see whether this also makes sense without using the formula. What would be the factors of 2 by 3? Take a few seconds. Think about what would be factors of 2 by 3. Anything that's a factor of 2 by 3, when it divides it, is going to give you an integer as the quotient. So factors of 2 by 3 will be 2 by 3 divided by integers. So let's list down factors of 2 by 3. 2 by 3 by 1 is 2 by 3. 2 by 3 by 2, that is going to be equal to 2 by 2 into 3, which is what is going to be this value, which is going to be equal to a 1 by 3, which is going to be 2 by 3 into 3, 2 by 4 into 3. So these are all the values that you get. Let's repeat the same process for 4 by 9. 4 by 9, 4 by 9 is by 1 is a factor of 4 by 9. 4 by 9 by 2 into 9, which is going to be equal to 2 by 9, which is going to be a factor of 4 by 9. So this is a 2 by 9 and this number is also a 2 by 9. 2 by 9 is a factor common to both these numbers. Now, is 2 by 4 by 9 larger or 2 by 9 larger? 4 by 9 is obviously larger. When you're writing down factors in this order, as we move towards the right, the value keeps decreasing. We are interested in picking up the highest common factor. The first such factor that you get, common factor, is obviously going to be the highest common factor when we are talking about fractions. These numbers landed up as 2 by 9 as we found out by listing down factors, which is what the formula also gave us. Doing something right. Quickly see it in a printed form. HCF of the numerators is a 2. LCM of the denominators is a 9. So the HCF is what the formula denotes as. Second property. When it comes to LCM and HCF, product of two numbers is always going to be equal to the product of the LCM and HCF of these two numbers. Let's take two numbers to be A and B, and let the LCM and HCF be L and H. So A into B is going to be equal to L into H. Let's look at the numerical example. Let's take these two numbers to be 20 and 24. The product of 20 and 24, 20 into 24 is equal to 480. Let's find out the LCM and HCF of these two numbers. Prime factorize both these numbers. 20 prime factorizes as 2 square into 5. 24 will prime factorize as 2 cube into 3. LCM, list down all prime factors 2, 3, 5. The respective highest powers 2 cube into 3 into 5, which is equal to 120. We computed this a little while ago. HCF is equal to, pick only the common prime, which is equal to 2, in its lowest power, which is equal to 2. So the LCM is 120, HCF is equal to 4. So 120 into 4 is the same 480. So the product of two numbers is always going to be equal to the product of the LCM and HCF of these two numbers. We have written this rule. We have taken a numerical example and checked out why it works, how it works. We'll check out why it works. I'm going to use the same numerical example. 20 prime factorized as 2 square into 5. 24 prime factorized as 2 cube into 3. The LCM, what all did we pick? We picked a 2, 3 and a 5 in the respective highest powers. So 2 cube into 3 into 5 was our LCM. So what all went into the LCM? I'll scratch those out. This went into the LCM. So did this. So did this. So these three numbers are now part of your LCM. What went into our HCF? Only common primes, which is 2, in its lowest part, which is a 2 square. That went into HCF. So between the LCM and HCF, we have divided all of the prime factors that we had between these two numbers. So either you multiply it as 2 square into 5 into 2 cube into 3, or you multiply it as 2 cube into 3 into 5 into 2 square. It's going to be the same. So again comes back to the definition of how we found out the LCM and HCF. HCF, we picked only common primes in their lowest power. So if a number is a prime of both these numbers, we pick the lowest of the two powers here. For LCM, what did we do? We picked all primes in their respective highest power. So all the primes featured here. And if the prime was available in more than one of these numbers, if it was available as part of two numbers, we picked the higher of the values here. So all of these prime factors in there have got counted between the LCM and HCF. That is why this works. Again, recapping what the rule is. Product of two numbers A and B will always be equal to the product of the LCM and HCF of both these numbers. Two things about this. One, will it work only for integers or will it also work for numbers which are not integers? It will work for even numbers which are fractions. Pick the example that we had. Try it for yourself. Find the product of those two numbers, 2 by 3 and a 4 by 9, and then check out whether the product of the LCM and HCF of these two numbers matched what you got with this. It will work for this fractions also. This is point number 1. Point number 2, this rule works perfectly well when we are talking about two numbers. It may or may not work beyond two numbers. So do not extrapolate thinking that A into B into C, is it equal to the LCM of ABC into HCF of ABC? It need not be the case. It will work perfectly for two numbers, but not for anything more than two numbers. So it's property number 2. Let's move on to the third one. Two numbers are said to be co-prime or relatively prime if they have no factor in common. Say we pick a number like 25 and 27. Is there any factor common to these two numbers? Factors of 25 are 1, 5 and 25. Factors of 27 are 1, 3, 9 and 27. There's no factor common between these two numbers. So these two numbers are said to be co-prime. The only factor common to them is 1. That happens to be the HCF. The HCF of two numbers is 1. Then those numbers are co-prime numbers. From this property that we learned a little while ago, product of two numbers A into B is equal to L into H. If H is equal to 1, then A into B should be equal to L. So if two numbers are co-prime, the LCM is going to be nothing but the product of the two numbers. There are 3-4 other useful properties about co-prime numbers. Let's quickly run through them. Two prime numbers will always be co-prime. That's very evident. Number is defined as a prime number if it has got exactly two factors. Let's take a 13 and a 17. What are the factors of 13 and 17? 1 and 13, 1 and 17. The only factor common to them is 1. So these two numbers will definitely be co-prime. Is it only two prime numbers that can be co-prime? Need not be. A prime number and a composite number may be co-prime, right? Look at this verb. It is not will, it is may, right? Some of them may be, some of them may not be. Let's look at an example again. 5 is a prime number, 9 is a composite number. The only factors of 5 are 1 and 5. For 9, the factors are 1, 3, and 9. The only common factor is 1. So a prime number and a composite number may be co-prime. Can two composite numbers be co-prime? Certainly yes. The first example that I walked you through, 25 is a composite number, so is 27. The only factor common to them is a 1. So those two numbers are also co-prime. Another very important rule, very important property. Two or more consecutive integers will be co-prime to each other. Let's take an example, 25 and 26. I'm not taking a 2 and 3 because 2 and 3 are anyway prime. These two numbers are composite numbers. They are consecutive integers. These two numbers, look at the factors, 1, 5, 25. Factors of 26, 1, 26, 2, 13. Is there any factor common between these two numbers? The only factor common to these two numbers is 1. So two consecutive positive integers will always be co-prime. We've seen this property. We've checked it with one example. But why should it work for all numbers? Just because it worked for this example, I might have picked one example where it worked. Let's figure out why this is working the way it's working. Let's start with 25. Any factor of 25, when it is trying to, f is a factor of 25. When it is trying to divide 26, can it be a factor of 26 if it divides 25? When it divides 26, it's going to leave you with a remainder of 1. 26 divided by 5, quotient is 5, remainder is 1. 26 divided by 25, quotient is 1, remainder is 1. The only factor of 25 that will leave you a remainder of 0 when it divides 26 is obviously 1, which means the only factor common to them will always be 1. So for two consecutive integers, if f is a factor of, let's say, the first integer, when it's dividing the second one, it necessarily will leave you with the remainder of 1. So two or more consecutive positive integers will always be co-prime. Extending the logic, two or more odd consecutive positive integers will also be co-prime because they will also have no factor in common. Let's move on to the third property. For any two numbers, this is again a very, very useful one. LCM is always a multiple of the HCF. Let's just figure this out. LCM, let's take two numbers, A and B, and let their LCM and HCF be L and H. LCM is a multiple of A and it's a multiple of B. So the LCM as a number will be divisible by A and will also be divisible by B. That is established. H is a HCF of A and B. H is a factor of B, which means we can write A as some X into H and B as a Y into H. So let's replace this A and B with XH and YH. So the LCM is going to be divisible by a multiple of H and another multiple of H, which essentially means that the LCM is divisible by H, which translates to the fact that the HCF will be a factor of the LCM or the LCM will be a multiple of the HCF. This is a very useful property. When you're trying to find out, can two numbers be LCM and HCF, you'll always have to make this check to figure out whether the HCF is a factor of the LCM. Quickly see it with an example after listing down the properties that we stated. Let the LCM and HCF of these two numbers be A and B, of the two numbers A and B be L and H respectively. What I said is H is a factor of both A and B, as we realized. A and B are factors of L, which means a factor of a factor is going to be a factor of the original number. So H is going to be a factor of L, or L is going to be a multiple of H. I wanted you to solve. Take 30 seconds for it. The product of two numbers is 96. Can their LCM and HCF be 16 and 9? First test is the product of the LCM and HCF equal to 96. 16 into 6 is equal to 96. It passes the first test. The second test, is the HCF a factor of the LCM or is the LCM a multiple of the HCF? 16 is not a multiple of 6. Therefore, 16 and 6 cannot be the LCM and HCF of two integers whose product is equal to 96. Let's move on from here. Move on, taking you to the most important part of this entire exercise. Many times we'll have to figure out when to use the LCM and when to use the HCF. We have learned what LCM is, we have learned what HCF is. Let's now find out when will we use HCF. What kind of questions will demand a HCF? Quickly run you through the exercise that you have done in finding out the HCF of these numbers. For sake of recap and clarity, factors of 36, other than 36, any factor of 36 is going to be a number that's smaller than 36. Same goes for 48. The listing down factors of 48, other than 48, any factor of 48 has to be a number smaller than that. So when you're listing factors, what we're actually doing is we're breaking a number into smaller parts. So keep this idea in mind. So what will be the kind of wordings that you'll see when you're trying to use HCF as a method to find the solution to a question? It is going to be something like this. HCF is used when we create sets out of two things, such that all sets have the same number of each of the things. To give an example, let's say farmers in Punjab pack wheat in 36 kg packs, and farmers in Andhra pack rice in 48 kg packs. You want to break both of these things into smaller packet sizes. So you're going to be breaking 36 into numbers which can divide 36. So you'll break it as 1, 2, 3, 4, 6, 9, 12, 18. These are all probably your packet sizes. When it comes to 48, any of these numbers could be your packet sizes if you want to break it down into smaller packets. If the packet size of both rice and wheat have to be same, then you're going to be picking only those numbers that will divide both 36 and 48. If you want to find out what is going to be the weight of the largest such packet size, that's going to be a 12. So you're breaking things down into smaller pieces. You're creating sets out of them. And each of the sets will have to be of the same value. Then you're going to be going for HCF. So look for these keywords. Quick guideline is you're going to be factorizing it. You're breaking things into smaller parts. So if you estimate that you're breaking two or more things into smaller parts, you're dividing them, you're distributing them, then the question that we are talking about is a HCF question. Two typical examples for it and then take it forward to LCM. One, the Elite Hotel has 27 treadmills and 18 elliptical machines. This word, keyword, right, divides them up into several identical exercise rooms located throughout the hotel. The exercise rooms are identical, so it's breaking it into sets which are equal, with no exercise equipment left over. So there is no remainder after dividing this 27 and 18. What is the greatest number of exercise rooms the hotel can establish? The hotel has got n exercise rooms. And let's say it's putting X treadmills into each of these rooms. Is going to be equal to 27. It's going to have n exercise rooms, going to put Y elliptical machines in each room. N into Y is going to be equal to 18. Does this make sense? Where n is the number of exercise rooms. So n is a factor of 27, n is a factor of 18. So n is a common factor to both these numbers. We're trying to find out the greatest number of exercise rooms possible. So we're trying to find out how high n can be. So this question obviously is a HCF question. Right? Let's move on to another example. Whitney has 25 decorative plates and 20 medals. She wants to display them in groups. She's breaking them into sets, into groups throughout her house, each with the same combination, right? This identical, same. These are keywords to note when we are talking about HCF questions of plates and medals with none left over. So obviously we're going to be dividing them into numbers which are going to be factors. They're divisible properly. Number of groups that Whitney can display. Let's go with the same thing. Let's say Whitney makes n groups out of these. X plates to each group. So n into x is going to be equal to 25. Same logic, n into y is going to be equal to 20. N, the number of groups that she makes, is a factor of both 25 and 20. Greatest number of groups. So it's not just a common factor, it's a highest common factor. So this question is also a HCF question. So you always look for that you're distributing it, dividing it, breaking it into sets of identical capacity, identical size, identical numbers. Let's move on to LCM. Quickly look at what an LCM is. Multiples of 2, 2, 4, 6, 8, 10. We're talking about multiple. We're talking about things repeating with a periodicity. Multiples of 3, 3, 6, 9, 12, so on and so forth. Common multiples, 6 and 12. The first such common multiple is the 6. Take a very simple example, again to consolidate this idea. Let's say every other day I jog in the park, and every third day I have an ice cream. Let's say on day 0, I jogged in the park and had an ice cream. When will both these events coincide? So on day 2, 4, 6, I'm going to be jogging. On day 3, 6, I'm going to be having an ice cream. On day 6, after today, I'll be having an ice cream and will also jog in the park. So you have an event repeating with some periodicity at a reasonable interval, time interval. Second one appearing with a different interval. You want to find out when these two events coincide. That's when we use LCM. So look at it again in terms of what kind of questions will use LCM? When things repeat, you're doing it multiple times, and you want to find out when these actions occur together. What are the words to look at? When you look at things which are going to happen multiple times, when things are going to repeat, when they occur more than once, and you want to find out when there is a common meeting point. Those are the questions when we'll use LCM in a question. So look at a couple of examples again to consolidate this idea. David goes fishing every 5th day. Brian goes fishing every 7th day. If David and Brian went fishing today, after how many days will they go on fishing again on the same day? Let's say today is day 0. For David, he's going to be going fishing every 5th day. So multiples of 5 is when he's going to go out fishing. 15, 20, 25, 30, 35. When it comes to Brian, starting today, it's going to be the 7th day, 14th, 21st, 28th, 35th. So when there is a number which is both a multiple of 5 and a multiple of 7, both of them will go out for fishing together. So multiples of 5, multiples of 7, common multiples. This question is an LCM question. Let's look at one more example. Teresa is arranging black marbles in groups of 13. So she's going to make it into packets of 13. And purple marbles in groups of 25. If she has the same number of black and purple marbles, let's say she's making X group of black and Y group of purple, 13X should be equal to 25Y, should be equal to some number. So this number is going to be a multiple of 13 and this number is going to be a multiple of 25. So this number is a common multiple. What is the smallest such number of marbles possible? The first such common multiple, which is the LCM of these two numbers. So you've got a hang of when you'll use LCM. You're repeating things. You're going to make it into sets of 13, 13, 13. You're going to be going fishing every 5th day. So if you repeat events, then you talk about multiples. We're going to talk about common multiples. First such common multiple. So this kind of wraps up the theory part of LCM and HCF. Quickly recap it before we get into the problem sets. Going to stop sharing for a while. Right. We started the day by understanding what HCF is, what LCM is. I'll do a 30-second recap of the method for both these things to find out how prime factorize these numbers. That's the first step. Having prime factorized, when it comes to HCF, the step that you're going to be doing is you're going to be picking only common primes out of them and in their lowest par. Product of common primes in lowest par will give you the HCF. Product of all primes in the respective highest par will give you the LCM. So this is how to find out the LCM and HCF. From there, we looked at properties of LCM and HCF. Can we find out LCM and HCF for fractions? Yes, we can. How do we go about it? LCM of fractions is find the LCM of the numerators and divide it by the HCF of the denominators. But before you venture out to doing that, bring both those fractions or as many fractions given to you in their lowest form, least form, irreducible form. To find out the HCF, the process is find the HCF of the numerators and divide it by the LCM of the denominators. The second property that we had is product of any two numbers will be the same as the product of the LCM and HCF of both those numbers. Will it work only for integers? We realized I asked you to take this exercise and try it out. It will certainly work for numbers which are even non-integers. It will work for fractions as well. The third property that we had, we essentially said that the LCM of two or more numbers will always be a multiple of the HCF of the numbers. We looked at why it worked. because HCF is a factor of A and B, the two numbers we are talking about. A and B will be factors of LCM because it's a multiple of both these numbers. So LCM has A and B as factors. A and B have H as a factor, which means that H is going to be a factor of L. So if someone tells you that L is an LCM and H is a HCF, do this test to check out whether H is a factor of L. And finally, we looked at what are coprime numbers. If two numbers have one as the only factor common between them, then those two numbers are called coprime numbers. Two prime numbers will always be coprime. Two composite numbers may be coprime. A prime number and a composite number may be coprime. One very important property from this which you need to note is basically this. Two or more consecutive positive integers and two or more odd consecutive positive integers will always be coprime to each other. Right? So this sums up the theory behind it. We also looked at when we'll use LCM. LCM will be used when things repeat with a periodicity. We're trying to find out when these two events are going to meet at a point. We'll use HCF whenever we're going to break things into smaller parts. We are factorizing them. That's when we'll be using HCF. Right? Enough of theory. I'll switch back to sharing. Got 4 questions in problem solving and 4 questions in DS. The problem solving questions, you might be able to do it in less than a minute, most of it. DS, when we come to it, exercise caution. Things that might look obvious are generally not necessarily obvious when it comes to DS. Just give me a minute to share the screen with you of the PS questions. A minute to solve this question before I get around to solving it for you. Right? Did you guys get the answer? How many of you got 8 as the answer and how many of you got 95 as the answer? Let's quickly run through the process. 136 blue marbles, 192 red, a lot of these numbers are given, must be packed into packets containing equal number of marbles. So basically breaking these into smaller packets, factorizing it. So obviously we are talking about a question which is a HCF question. Let's also check it as we proceed along. With packets containing only marbles of the same color. So if I put it into a packet blue marbles, it can contain only blue marbles. I should not mix marbles. That's the idea. What is the minimum number of packets required? That's what we'll have to find out. 136 blue marbles. Let's say I'm putting n marbles into a packet and I get a packets out of it. N into a is going to be equal to 136. Quickly run through this process. 192 red marbles. I'm going to put n marbles into it because each of these packets should contain the same number of marbles. N into B. 72 is equal to n into C. 216 is equal to n into D. And 144 is equal to n into E. So n, the number of marbles in each of these packets, is a factor common to both all of these numbers. The larger the value of n, smaller the value of a in this number. We are looking at the minimum number of packets. So we need the least possible value for a plus b plus c plus d plus e. Which essentially means that we need to minimize each of these numbers. Consequently, it means that we need to maximize n. N is a factor common to all these numbers. And we need to maximize that factor. Boils down to finding out the HCF of all of these numbers. Start by prime factorizing them. 137 is an 8 into 17. So that becomes 2 cubed into 17. You need to be comfortable doing this step. The longer you take, the more the time you will be taking. And you may not be able to finish the quant section in time. 192 is a 192. I'm struggling right now. It's 96 into 6. Or let me go with the 24 into 8. Which is nothing but a 64 into 3. So that is going to be 2 power 6 into 3. Right. 72 is a 9 into 8. Which is nothing but a 2 cube into a 3 square. 216 is a 24 into 9. Which is nothing but 2 cube into 3 into 3 square, which is 2 cube into 3 cube, 6 cube it is. 144 is a 16 into 9, which is 2 power 4 into 3 square. Let's pick the only prime factor that's common to this, which happens to be a 2, and in its lowest part, which is equal to 3. So the HCF of these numbers is equal to an 8, which is nothing but the value of 8. Now n. N is what? The number of marbles that you find in each of these packets. There's a good chance 8 is going to be choice number 1 if it is presented to you as a multiple choice question. The question is not about how many marbles went into each packet. It is about what is the least number of packets that you can have. If I have 8 marbles in the first packet, I'll have 17 such packets. If you have 8 packets, 8 marbles into this, I'll be having 24 such packets. I'm listing down the packets on the left hand side. 17 here, 24 in this case. Number of packets here will be equal to 9. Number of packets in this case is equal to 24, and the is equal to 27. I'm sorry. The number of packets in this case is equal to 18. So how many total packets will we have? 27 plus 18, which is equal to 45, 54, 78, 95. The number of packets, least number of packets required to pack all of these marbles is equal to 95. So find out the HCF to find out how many marbles went into it, and subsequently find out the number of packets. The key takeaway is watch out for what is to be found out. If you had found out the answer to be an 8, you did everything and got the answer wrong. The question is not about how many marbles went into each packet. The question was how many packets were required. So move on to question number 2. Sure, my colleagues will have shared the question with you. So I'll get around to solving it because we need to wrap this session up. X and Y are two distinct positive integers. Every time you read these things, right, these adjectives make a lot of difference to your final answer. These two numbers are not same, they're distinct. Their sum is equal to 360. What is the largest possible value of the HCF of these two numbers? Let's set about writing a framework for it. Numbers are X and Y. X plus Y is equal to 360. These two are distinct numbers, so there's nothing common between them. Let's say the HCF of these two numbers is H. So we can write X as an AH and Y as a BH. So AH plus BH is equal to 360, which is H into A plus B is equal to 360. Look at it this way. H is one number, A plus B is another number. Product of these two numbers is equal to 360. We're trying to find out how high can the value of H be. It can technically be as high as a 360 and an A plus B can be a 1. But that doesn't make sense because if X and Y are distinct positive integers, A and B will also be distinct positive integers. You cannot have the sum of two distinct positive integers being a 1. So this is ruled out. So let's start the other way around. Let's find out how low can the value of A plus B be so that the value of H gets maximized, because the product of H and this A plus B is equal to 360. If this has to be maximized, consequently we can achieve it only when we minimize A plus B. How low can the values of A plus B be? The least value possible for A is a 1. The least value possible for B is a 2, because these have to be distinct numbers. So if this is a 3, the value of your HCF is going to be equal to a 120. The highest possible value, the largest value possible for the HCF of these two numbers is equal to 120. So what will these two numbers be? One number is 120. The other number is equal to 240. Their sum is a 360 and their HCF is a 120. Key takeaway, track keywords, right? If you had thought of these numbers as not distinct, if you had not read that properly, the answer that you might have got would have been a 180. You would have taken A plus B into H is equal to 360. If you went with 1 and 1 for A and B, the answer is obviously 180. And that is likely to be one of the answer choices. Every time you read, underline these things, mark these things on your scratch paper before you proceed further. Third question. It's a beautiful question, very good question. On the face of it, it looks like a reminder question. Yes, it has got reminder concept, but more importantly, it's a question which is much more than a reminder question. What's the smallest number that leaves a remainder of 2 when divided by 3? 3 when divided by 4, 4 when divided by 5, 5 when divided by 6, and 6 when divided by 7. Let's look at how to go about it. Whenever you start a reminder question, a good starting point is to write these things in a standard framework for reminders, which is the number, let's say, is an X x when divided by 3 leaves a remainder of 2. So x is going to be a number which is a multiple of 3 plus 2. Right? It's going to leave a remainder of 2, and it's when divided by 3, which means you divide this number by a 3. 3a by 3 is going to leave no remainder. 2 by 3 will leave you with a 2 as a remainder. So this is the standard framework. The same x leaves you a remainder of 3 when divided by 4. So that's going to be equal to a 4b plus 3, a 5c plus 4, a 6d plus 5, a 7e plus 6. So x basically is all of these. Now let's just look at one example for it. Can x be a 5? Just to satisfy the first condition, right? Divide 5 by a 3. It's going to give you a quotient of 1 and a remainder of 2. So it satisfies it. Let's see if we can write it a little differently, and let's see if that will give us some idea. Can I say if x is a 5, can I say when divided by 3, it gives me a quotient of 2 and a remainder of -1? Does it make sense? If 5 is nothing but a 3 into 2 minus 1. Ideally, you and I would have said if 5 is nothing but a 3 into 1 plus 2. That's how we normally write. The quotient is 1, but if I force fitted a quotient of 2, the remainder becomes a -1. So can we say 3a plus 2 as a remainder? This is a multiple. If I had added one more to it, this number would have got divided by 3. 3a plus 2 plus 1 will certainly be divisible by 3. So this is nothing but a 3f minus 1. Similarly, look at this. This number when divided by 4 leaves you a remainder of 3. If I had increased the quotient by 1, a number, let's say, is 7, can leave a remainder of 3 when divided by 4, or it can leave a remainder of -1 divided by 4. If it's going to leave you a remainder of 3, it's the same as saying this is a 4g minus 1. This number is a 5h minus 1. This number is a 6k minus 1. This number is a 7m minus 1. So what we have is we have an x which is a multiple of 3, 1 less than that. It's a multiple of 4 and 1 less than that, so on and so forth. Take the 1 from all of these equations to the left hand side. So what we'll have is x plus 1 is 3f, x plus 1 is 4g, is 5h, is 6k, is 7m. Essentially boiling down to saying that x plus 1 is a multiple of 3, it's a multiple of 4, 5, 6 and 7. So x plus 1 is a common multiple of all of these numbers. Let's find out the least possible value for x plus 1, which is as good as finding out the LCM of these numbers. LCM of 3, I'm prime factorizing the numbers as we are writing it. So I'll write it in the next string. LCM of 3, 4, 5, 6, 7 is what we need to find out. So I'm going to prime factorize the numbers as we write it, which is 3, 2 square, 5, 2 into 3 and 7. To find the LCM, we'll list down all the prime factors, which is 2, 3, 5 and 7. Respective highest powers, which is 2 square into 3 power 1 into 5 into 7. 2 square into 3, 12, 5s are 60 into 7, which is equal to 420. Is x 420 or x plus 1 420? X plus 1 is equal to 420. So x is equal to 419. The smallest number that would satisfy all of these conditions is 419. So it did involve concepts about reminders. But more importantly, what we used to find the final answer is the LCM of these numbers. So move on to the next one. The key takeaway for this question, start any reminder question with the standard framework and then proceed from that. Might give you an idea as to how to crack the question. If the product of two positive integers is 144, which of the following could be the LCM and HCF of these two numbers? Mark all answers that are correct. Right. Product of two numbers, A into B, is going to be equal to the product of the HCF and LCM of these two numbers. It has to pass this test, which is test number 1. The second test that it has to pass is that the LCM is going to be some multiple of the HCF. Unless both these tests are passed, this pair is not going to satisfy the condition. Let's quickly check out for each of these things. 72 and 2 is a product equal to 144, passes condition number 1. Condition number 2, is 2 a factor of 72? Certainly yes. So this is one set which will work. 48 and 6, the product is not equal to 144. Even if one of the conditions fails, you don't have to bother about it. 18 and 8, product is equal to 144, satisfies this condition. Is 8 a factor of 18? No, so this is not going to work. 24 and 6, product 144. Is 6 a factor of 24? Certainly yes. 16 and 9, product 144 passes this test. Is 9 a factor of 16? No. So the pairs that will work are basically 72 and 2 and 24 and 6. So almost done with the problem solving part. The two takeaways from this question: product of the LCM and HCF is equal to the product of the two numbers. Second one, HCF of two numbers is always a factor of the LCM of these two numbers. Brings to an end the problem solving questions. Let's move on to the more interesting one, which is the DS questions. For the uninitiated, these are the 5 answer choices. Any DS question is going to have a question followed by 2 statements. Statement 1 alone is sufficient, 2 is not, go with A. 2 alone is sufficient, 1 is not, go with B. Each is independently not sufficient, but together they are sufficient, go with C. Each of the statements is independently sufficient, go with D. Data is not sufficient, then go with E. Start with the first question. X is a positive integer. What is the value of X? So we need to find out the value of X. Whenever such questions are asked in data sufficiency, first and foremost thing, keep this in mind. The data is sufficient if you're able to get a unique value for X. Should be able to say X I know is 14, X is 21. You need to be able to come up with one single number. If you say X can be a 4 or an 8, then the data is not sufficient. We'll start evaluating statement 1. LCM of X and 72 is 144. LCM is 144. Let's prime factorize the LCM as the first part. 144 is a 16 into 9, which is 2 power 4 into 3 square. Which means between X and 72, the number should have brought in, one of the numbers should have contained a 2 power 4 and another number should have contained a 3 square. The same number could have contained both also, which is not a problem. But one of the numbers, because the definition of LCM is it has all the prime factors in the respective highest power. So highest power of 2 that we are going to be finding between these two numbers is a 2 power 4. The highest power of 3 that we'll be finding between these two numbers is a 3 square. So 72, let's prime factorize and check out. What did it bring to the table for the LCM? 72 is an 8 into 9, which is 2 cube into 3 square. So 72 has probably contributed to 3 square, no issues at all. But 72 had only a 2 cube in it. So it did not bring the 2 power 4 to the LCM. So what should have brought the 2 power 4 to the LCM? X should have brought the 2 power 4 to the LCM. So X should be at least 16. Can it be anything else? Is 16 the only value possible for it? Can be a 16, certainly yes. What if it is 16 into 3? If the X is equal to a 2 power 4 into 3 and 72 is a 2 cube into 3 square, obviously we'll write down all the prime factors, which are 2 and 3. We would have taken the highest power of X as a highest power of 2 as a 4 from X, and we have taken the highest power of 3 as a 2 from 72. So X can be a 2 power 4, or X can be a 2 power 4 into 3, or X can also be actually a 2 power 4 into a 3 square. So it could be any one of these 3 values, which is essentially it could be a 16, or it could be a 48, or it could be a 144. In all of these 3 instances, this number and 72 is going to return the same LCM, which is equal to 144. Because we are not getting a unique value from it, statement 1 alone is not sufficient. Immediately, let's scratch out answer choices A and D. What we are down to is choices B, C, or E. Let's evaluate statement 2 alone. 2 alone says the HCF of X and 72 is an 8. We'll prime factorize the HCF first. HCF is equal to 2 cube. Let's quickly do the same job for 72. 72 is equal to a 2 cube into a 3 square. So this is what we have. HCF is the only factor common to both these numbers, which means that the X should definitely have a 2 in it. And HCF will contain the common prime factor in its lowest power, which means X should have had at least a 2 cube in it. Otherwise, this HCF will not be able to divide it. So HCF, X is definitely going to be at least an 8. Is that the only value possible for it? X could be any multiple of 2 cube other than having 3 as a factor in it, which is X could be 2 cube into, let's say, a K. K should not contain any 3 in it. Then the HCF of X and 72 will certainly be an 8. Let's look at this. I'll go with a K as a, let's say, a 5. 2 cube into 5 is equal to x, for example. What is the only prime number common to both these numbers? It's 2. What is in its lowest power? Which is the 3. So 2 cube is the HCF of both these numbers. So x we said possibly could have been an 8. X we realized can be a 40. It can be any multiple of 8 as long as that multiple does not contain 3 as a factor in it. So again with statement 2, we are not getting a unique value for x. So statement 2 alone is also not sufficient. When we started evaluating this statement, we were down to choices B, C or E. Cancel B as well. What we are down to is C or E. Combine the two statements. We know the LCM is equal to 144. We know the HCF is equal to 8. We know these two numbers are 72 and x. Product of two numbers is equal to the product of their LCM and HCF. Don't waste time trying to find out what this x is. Don't compute the value to be a 16. You know that this value is going to be unique. Statements together are sufficient. Choice C is the correct answer. Key takeaway, find counterexamples. It's a very useful way of negating a statement, invalidating a statement in DS. Second thing, we're repeating it the nth time, product of two numbers is equal to the product of the LCM and HCF of these two numbers. Let's move to the second one. This is more of a word problem. If A and B are positive integers, what is the HCF of A and B? We need to find out HCF of A and B. Question mentions these are positive integers. Again, it's asking you for a value of A and B. The data is sufficient when we're able to come up with a unique answer to it. Start with statement 1. The product AB is A more than the square of A. We'll frame an equation for it. Product AB is A more than the square of A. Right? This is the equation that translates to. So AB is equal to A into A plus 1, right? Which is A square into A. So this essentially boils down to the fact that if A and A are equated here, B is equal to A plus 1. So what do we have? We have one number A and we have B, which is equal to A plus 1. Translates to the fact that these two numbers are consecutive positive integers. Consecutive positive integers are always co-prime, which means the HCF of these two numbers is going to be 1. So using statement 1, we could get a unique value for the HCF. Statement 1 alone is sufficient. Choice A or D is going to be the answer to this. Let's move on to statement 2 and check out whether that is sufficient to decide between A and D. Twice the value of A, let's start writing it. 2A is equal to 1 less than the sum of A and B. Sum of A and B is A plus B. Twice the value of A is 1 less than the sum is what it says. Let's take A to the left hand side. This makes it as A is equal to B minus 1 or B is equal to A plus 1. We're coming back to what we got with statement 1. One number is A, the second number B is equal to A plus 1, which means these two numbers are consecutive positive integers. Their HCF is going to be equal to 1. Statement 2 alone is also sufficient. Choice D is the correct answer to this question. So move on to the key takeaway. HCF of two consecutive integers is 1. Move to the third question. It's a very interesting question. Involves concepts about factors. If A is a positive integer, what is the HCF of A and 32? We again need to come up with a unique value for the HCF. Otherwise, the data is not sufficient. We need to find out the HCF of two numbers. One of the numbers is 32. So I'll quickly prime factorize it. That number is equal to 2 power 5. Right? 32 prime factorized is 2 power 5. The only prime factor that 32 contains is 2. Let's have this perspective in mind. A has exactly 3 factors. What kind of numbers will have exactly 3 factors? A prime number will have exactly 2 factors. Square of a prime number will have exactly 3 factors. Right? Square of a prime. Let's take a prime as a p. Square of prime is going to be equal to p square. 1, p and p square are the only 3 factors for this number. Typically, how will prime numbers be? Prime numbers are usually odd with the exception of only one prime number, which is a 2. So trying to find out the HCF of an odd number and 32 in one instance, or we might be finding out the HCF of 2 and 32. These are two possibilities. An odd number does not have 2 as its factor at all. 32 has only 2 as its factors. So will there be any factor common between these two numbers? None. So if this happens to be the case, the HCF is equal to 1. Conversely, if the prime number ended up being a 2, this is the only exception. This is the only case which spoils the broth for us. In this case, the HCF is going to be equal to 2. So do we have a unique answer with statement 1? No. Statement 1 is not sufficient. Let's rule out choices A and D. Let's look at statement 2. Much more interesting. 2A has twice as many factors as A. A has got, let's say, X factors. 2A has 2X factors. The number of factors doubles when you're multiplying this number with a 2. Let us start with the premise that this number A already had a factor of 2 in it. Let's go with some example. Let's take this number to be a 2 into 3. Let's say A is equal to 2 into 3. How many factors will it have? To find the number of factors, let's increment the powers by 1 and then multiply it, which is going to have a 2 into 2. Number of factors, if A is a 6, is going to be equal to 4. What is 2A? 2A is going to be equal to 2 square into 3 power 1. Increment these powers by 1. That's going to be equal to a 3 into 2, which is going to be equal to 6. Did the number of factors double? No, it did not double. It just became 1.5 times. It increased by just 50%. Let's take another example. Let's take something like a 21. If A is equal to 21, which does not contain even a single 2 in it. So 3 into 7 is how it prime factorizes it. Number of factors for this number, increment the powers by 1. It's going to be a 2 into 2, which is equal to 4. Now 2A is going to be equal to a 42, which is going to be equal to 2 power 1 into 3 power 1 into 7 power 1. Now increment the powers becomes 2 into 2 into 2, which is equal to 8. Number of factors doubled. If the original number did not have even a single 2 in it, if 2 was not a factor of it at all, when you're adding 2 as a factor for the first time in 2A, you're adding 2 here. Any other thing, a 2 to 3 is only a 50% increase. A 3 to 4 is only a 33% increase. The times it increases is lesser than 100%. The only time it will become 100% is when the original number did not have 2 as a prime factor. So what can we deduce about A? A is a number which does not have 2 as a factor, which means A is an odd number. HCF of an odd number and 32 is always equal to 1. So from statement 2, we have a unique answer. So statement 2 alone is sufficient to find the answer. 2 alone is sufficient. Choice B is the correct answer to the question. The last question. Finish the key takeaway. I seem to be forgetting it too often today. A prime number has exactly 2 factors. Square of a prime number has got 3 factors. Right? This is a beautiful question. Just give you 1 more minute to crack this before we discuss it, if you haven't already cracked it. Right. Let's get around to doing this question. This question is also finding out what is the HCF of these 2 numbers. So we need to come up with a unique answer, which is when the data is going to be sufficient. A and B are positive integers. Make a note of these things. Keep track of these. These are very important. Start with statement 1. HCF of 3A comma B is equal to 15. Right. Now, as I mentioned, a good way to look at whether a data is sufficient or not is to go with counterexample. I'm going to take that approach for this. Let's say A is equal to a 15 and B is equal to a 15, right? HCF of 3A, HCF of 3A, which is going to be equal to a 45, and a 15 is going to be equal to 15, right? So what do we know is the HCF of A and B? HCF of A and B in this example is 15 comma 15, which is equal to 15. So in this example, I've got an answer which is equal to 15. I have to strive to get the HCF of 3A comma B to be equal to a 15 and try and see if we can get a different value for this. Let's check out what happens when it's a 5. If A is equal to a 5 and B is equal to a 15, then the HCF of 3A, which is equal to a 15, comma B, which is a 15, is still a 15. HCF of A and B, which is HCF of 5 and 15, is equal to a 5. Do we have a unique answer with this? We got 2 different values. So statement 1 alone is not sufficient. We'll rule out choices A and D. What we are down to is B, C, or E. The gist of it, if you do not take an example, is essentially that between B and 3A, 15 is a common factor. So B is divisible by 15. That's a key inference that I can draw from it. B is divisible by 15. And I can also draw a key inference that 3A is divisible by 15. If 3A is divisible by 15, should A be divisible by 15? Not necessarily. A can be a number which is not divisible by 15, as we saw with the case of A being a 5. So one key takeaway from this particular statement, which we might use subsequently, is that B is divisible by 15. Let's move on to statement 2. What we are down to as answer choices is B, C, or E. Statement 2 tells us that A comma 2B is having a HCF of 30. Okay, let me start with a counter example. Let's start with this: A being equal to a 30 and B being equal to a 15. A comma 2B, HCF of A, which is a 30, and 2B, which is equal to a 30, is a 30. So condition holds good. What is the HCF of A and B? HCF of A and B is equal to a 30 comma 15, which is equal to a 15. Look for a counter example. A is equal to 30, B is equal to a 30 as well. HCF of A and 2B, A is a 30, 2B is equal to 60. HCF of these two numbers is a 30. This condition holds good. What is the HCF of A and B? HCF of A and B is equal to a 30. We don't have a unique answer with statement 2 as well. So statement 2 alone is also not sufficient. Let's rule out choice B from this. What we are down to is C or E. One key inference we can draw from this is that A has 30 as a factor. A is divisible by 30 is something that we can infer from statement 2. Let's combine the two statements and see whether it makes sense. From statement 2, we have inferred that A is divisible by 30. From statement 1, we have inferred that B is divisible by 15. And we know that A is divisible by 30, which essentially means that A has to be divisible by 15. That is something which we can take from statement 2 and add it to statement 1. If 3A comma 15, knowing very well that A is divisible by 15, has a HCF of only 15, 3 times A and B have a HCF of 15. We know very well that from statement 2 that A is divisible by 30, which means it's divisible by 15. And from statement 1, we know that B is divisible by 15. If 3 times A and B has a HCF of 15, the HCF of A comma B cannot be anything more than 15. It has to be a 15. Because A is divisible by 15, B is divisible by 15. 15 is definitely going to be a factor of these two numbers. The only worry that we had is it only 15 or is it going to be more than 15? If a larger multiple of A and B had a HCF of only 15, A and B cannot have a HCF which is anything greater than 15. Combining these two statements, we can infer that the HCF of these two numbers, A and B, is a unique value which is 15. So choice C is the correct answer to the question. Go through the last one once more. It's a beautiful question. Took a while to make that question, and it took a while to find a good explanation for this question as well. Right? No key takeaway right now. The key takeaway for you is what is the next session. Next session, we have scheduled it for first Friday of next month. We'll try and keep first Fridays as our dates with GMAT live sessions. September 1st, 2017 at 10 p.m. We've done 2 sessions on math, data sufficiency, once with our sister concern, 2 IIM, and today we have done number properties. Let's move on to a bit of verbal. We're going to be doing critical reasoning on that day. And it's not me. We'll be having Shweta running that session, who handles the verbals, entire verbal for us. Right? I want your feedback and topic suggestions for subsequent topics. Was the audio clear? Was the teaching methodology good enough? Do you want something that can be made better so that these sessions are useful, that you crack a lot of, you make this a part of your GMAT preparation and score high in the GMAT? Send an email to us with your suggestions. I'll definitely be happy to have your suggestions on learn@visaco.com. I need one favor from you guys. Go and subscribe to this channel. I need a lot of subscription so that we can get this process known to more people. Best wishes for your GMAT. Thank you guys. Crack your GMAT. Good night. Thanks for staying back late.